So thanks for the introduction, Mark. As he said, I'm here to talk about job processing. I think this is a really exciting and interesting topic that doesn't really get the press it deserves in the Ruby community. Everybody knows about Resque, everybody knows about Sidekiq, but much past that, it just kind of drops off into oblivion. So this is stuff I've been working on pretty much for the last year. So I'm really excited to get a chance to come talk to everybody about this. I'm excited to be here with an audience of actual people today. In preparing this talk, I've given it at home, I don't know how many times yet, but I think my dog is sick of hearing about job processing. So I'm really glad to have people here to listen. So obviously I'm Tanner. I work for Tapjoy out of our Boston office. For those of you not familiar with Tapjoy, we're a in-app mobile ad platform. So what does that mean? We have an SDK for mobile app developers that allows them to put ads, offers, other monetization options into their application so that users have ways to pay them that aren't just give me cash. Along with that, we've got about 450 million monthly active users. This is a big number. Because we're an ad network, that means we're dealing with lots and lots of requests, millions and millions of requests a minute. Things get hard. So what does that really boil down to? We're talking about scale, right? This is Big Ruby Conference. We're here to talk about scale. Let's talk about scale. This brings up interesting problems of scale, right? So anything we put into production goes out to this load immediately. That means the naive solution fails. Not in weeks or months. The naive solution fails in minutes. We have to avoid single points of failure. We have to have distributed systems from the start. We have to think about hard things up front immediately every time. I think this is really fun. I think these are really great problems to get to go solve every day, and I'm excited to get to share some of these things that we've been doing. So let's set the scene a little bit. So this all started way back in 2012. So what were we all doing in 2012? Where we were upgrading our apps to Ruby 1.9, we were watching Gangnam-style mashups, and waiting for the Mayan apocalypse. Outside of those things were going, really pretty well. I mean, everything was good. We were pretty happy with the way things were, mostly. Good news. We're an ad network. Our traffic is going up, way up. We're seeing month after month, quarter over quarter, huge increases in traffic. 50+% increases in traffic inside of 6-month spans. We're moving really fast. We're scaling up really big. This is great for us because more requests means more money, and we like that. But not everything is perfect. So our job system is starting to kind of show some issues. Predominantly during our high traffic periods, jobs are backing up. And not just a little bit, jobs are backing way up. We're seeing 10,000+ messages in queues that aren't clearing out. They'll stay that way until our peak traffic starts to trend back down, and finally we can get all caught back up. This is not awesome. And then secondly, we have kind of an event processing system, similar to what Coraline was talking about just a few minutes ago. And much like she was saying, these are important things to us. This data is really useful, but we've discovered that we're losing small amounts of this data. We don't know how much, and we don't know exactly where in the pipeline we're losing it, but we're dropping some of it, and that's real bad. And for the worst news, all of this is our fault because the job system and the event processing system are entirely homegrown. Emphasis on grown. These are the kinds of systems you discover one day are there, and you can tell no one sat down and thought hard and planned and prepared and set up a design review. This system just kind of accreted code over years, and now it's there in front of you, and it's a problem. Particularly to the job system, we can't scale up individual jobs. We can't identify that one job that's going slow and say, hey, let's make sure we can do more of those right now. Let's task more servers to do that. Let's task more processors to do that. We can't really do that in the way it's designed. And event processing. So let's talk a little bit about what event processing means to us. So for us, these are data points in our application. These are things like a user has seen an ad, a user has clicked an ad. If we're lucky, a user has converted on an ad, and that means we're getting money. This is good stuff. This is the core of our business analytics, our business intelligence system. And we generate a lot of those. This is on the order of hundreds and hundreds of thousands per minute, 500,000, 600,000 per minute. Lots and lots of these. And we're losing a very small percentage of that, but we don't know how many that is, and we don't know which ones we're losing, and that's bad. Part of the reason we don't know is that the way the system's designed currently, it's basically syslog. We write messages out to syslog. We have some custom log handlers that bundle and aggregate and do things to the data and then ship it off to our actual, data warehousing system. But syslog's kind of a mess, and it's really not easy to tell what's going on in there, other than sometimes you get exit codes that aren't 0, and that doesn't tell you much. So this is not awesome. It's time for us to do something about these problems. We're seeing all this growth. We're seeing all this coming up ahead of us. We can't stay this way. We've got to fix things. But change is hard, and where do you even start with a problem this big? We can't just dive in and go fix all of this all at once. These are big systems with lots of data. So we kind of need to figure out what's important to us first and what we really need to be approaching. And what we come down to is we're talking about message queues. We're talking about job processing. And when you start talking about that, you're really talking two components. A queue, something that takes data in on one side and lets data out on the other side. It's pretty simple. And secondly, you need something to take data out of that queue and do something meaningful to your application. Without that, it's just data flowing through a queue. That doesn't mean anything. We need something to make it mean something to us. So let's kind of break this down a little bit. So when we talk about queues, there's some choices. A lot of choices. You may be familiar with some of these terms. I wasn't familiar with all of these. I actually Googled these the other day, and there's just a crazy amount of them. I mean, I think most people in this room have probably heard of RabbitMQ or have seen Redis used as a queue, or maybe Beanstalk D if you're really up on some of the cool things in Ruby right now. But there's just a ton of choices. How do we even figure out which of these things is useful and meaningful to us? So we decide the same way we decide with every problem in computer science, right? We get 3 choices and we only get to pick 2 of them. Great. We do this every time, but here we go again. So in the case of queues, really there's 3 things that mattered most than anything else. We need durability, we need availability, and we need throughput. So let's break these terms down just a little bit. So durability, what do we really mean there? All we mean is I want to put a message in a queue, and I want to be reasonably assured I'm going to get that message back out. So we're talking about avoiding, maybe a disk failure or a process crash or the simple kinds of things that just happen every day in real systems. But we need to have an idea of how many of these we can see and what the likelihood that these messages survive is. Next, we're talking about availability. This is really critical. We're talking about, is this thing a single point of failure? Hopefully not, because we don't want single points of failure. We have big systems. But what kind of tuning can we do to that? How available can we make it? And what are some of the trade-offs in doing that? And then lastly, and somewhat obviously, how many jobs can I mash through the thing? Because we got a lot of jobs. We got a lot of data to move. How fast can we push this data in, and how fast can we get that data back out again? Because if it doesn't matter on all of these things, if it's going to take way too long, then that's not useful. We need to do this stuff fast. Oops. I guess that isn't the end. Right? We live in the real world, and things cost money. And at some point, we have to make trade-offs based just on how much will it cost to do these things. You can imagine, ideal scenarios where you can get blazing fast things that are always available and will never lose your messages, and it will cost you $10 million a server to have it. That's probably not feasible for most anyone in this room. That's not realistic. So we do have to consider cost, but it's not the top of our list. So for us, we narrowed that list down to 3 choices. These are based on both the criteria above and then, truthfully, like anyone else, things we were familiar with internally, things we had experience with and knew what to do with. That list was right there, RabbitMQ, SQS, and Redis. If you're not familiar with RabbitMQ, it's a blazing fast, really slick message queue that is flexible and can do almost anything you want to it. It's really, really neat stuff. SQS is Amazon's hosted queue system. It's a little bit less flexible, but it's really crazy available. And then lastly, Redis, because we're in Ruby and everyone has used Redis or Resque or Sidekiq, and we know how this works. We have Redis around for other things anyway. Maybe we can just use that. So breaking it down, Rabbit is really fast. It can be really, really incredibly fast. It can also be really, really durable. You can almost ensure that no message will ever get dropped, both putting them in or taking them back out. That's awesome. That's a really great feature. And it's pretty fault tolerant. The problem with all of this in the case of Rabbit is that's entirely in how you configure it. You can configure it to be completely non-durable, incredibly fast, and not fault tolerant at all. It's a choice. So it's a little bit complex and having to really understand how Rabbit fits together and how it works to make those choices fit what you want. Then there's SQS. It's incredibly durable. I don't know if it's as durable as S3, which Amazon claims like somewhere around the heat death of the universe, they'll have lost 1 bit of data out of it. S3, I don't think we're quite that durable, but it's pretty darn close. After that, it's incredibly available. I know Amazon gets knocked a lot for EBS and some of the failures and things they have there, but SQS actually tends to be the one thing that is always up inside of Amazon. And then lastly, it's not as fast. All of these things boil down to it's just not going to be quite as fast as Rabbit. That might be okay, it might not. We'll have to really look at the numbers to see. And then Redis. This is the one most people are probably familiar with, right? Redis is a key value-ish, data store-ish. It's the Swiss Army chainsaw of data stores, right? It can do anything and it can do some of those things well. It turns out that queuing probably isn't the thing it does best, but it's still really useful. It's really fast. I mean, I think everybody here has played with it enough to know that it is just an incredibly fast system. It's also reasonably durable. You can set, how long stuff will reside in memory before it gets flushed to disk and manage all of that. But remember, we're way back in 2012 here. The idea of Redis cluster or Redis Sentinel or any of the Redis clustering tools don't exist. Everyone is running around trying to figure out how to make that work. So we don't really have a good story in Redis about how to make it distributed, how to make it not a single point of failure. So that's a real problem for us. So what we ended up deciding is that really we did have 2 very distinct use cases for our queuing. We have our event processing case, which, as we've talked about, we really care about this data. This data is really important to us, so it needs to be very durable. Also, it's incredibly fast. We have a lot of this data coming in, so we need to be able to mash this stuff through the queue really, really quickly. Secondly, we have our just general purpose jobs. So when I talk about general purpose jobs, what I'm talking about are the things you always background in your web app. Oh, we need to send an email, or we need to make an HTTP call to a partner, or maybe we have this other thing that isn't terribly important, but it's really memory intensive, and we just don't want to do that interactively in the app. Or a thing that's incredibly failure prone, and we're going to want to retry 5 or 10 times, because it might take that many times to get right. These are the kinds of things we send off into jobs, and we have a lot of those too, but not quite as much as we do with the event processing stuff. Okay, so this is a Ruby conference. I've been up here rambling about queues. Let's talk about Ruby. I think that's what everyone would rather hear. So let's talk about job processors. Job processors. We got a lot of those too. There's not quite as many here as there are in the queuing case, but there's a lot of job processors in Ruby. So again, we have to figure out what makes sense and how we can fit these things in. Interestingly, in our case, we've already picked a queue. So we can really narrow this set of choices down to things that can work with the queues that we want to work with. And the answer is they don't. So in 2012, we looked at basically every job processor you can use in Ruby, and we discovered that pretty much none of them did what we wanted. So let's go build one or 2. So what is a job processor? What really is it at its core? It's really just 3 things. It's something that takes messages out of a queue. It's something that does some decision based on that message and finds a chunk of code we want to run, and then something that runs that code. That's it. That's all we have to do. This is easy. We're engineers. We can do this. Okay, but we're talking about scale here, right? Like this is big stuff. We can't just have one machine read from a queue and find a job and then run that job and do that one at a time on a machine. That's going to take a lot of machines to get through hundreds of thousands of these a minute. That's not feasible. So we need to run these jobs concurrently. Okay, well, we're in Ruby, so this gets a little bit harder, but we know how concurrency in Ruby works, so let's nail this. All right, so Ruby concurrency. We pretty much have three choices. You have forking, which has been around since the dawn of Unix. You spin up a child process and do things in it. Can't really talk back to the parent easily, but that's probably okay. Fibers. Fibers are the cool new thing in Ruby 1.9. We should totally want to use these because new stuff is always better. Fibers are really cool. Maybe we can make use of this. And then threads. We've been told forever that we can't use threads in Ruby, but maybe that's not true. We need to look at this and see. So let's talk about our Rabbit job processor. We really looked around at a lot of things, even played with a few that supported Rabbit, and really decided that just didn't really fit. So what could go wrong? We can handle this. So a little bit about how you interact with Rabbit. When you're interacting with Rabbit, it's highly asynchronous. You make a request for something, and it sometimes comes back later and tells you about it. When you tell it, hey, I'm done with this job, it'll tell you that it accepted that sometime later. So this is a really asynchronous thing. Because of that, all of the connections to Rabbit are also stateful. So that means the same connection that you open to receive a job is the same one you have to say you're done with the job on. So if we need multiple connections to be able to do this quickly, we have to be able to track all of those connections and which job matches with each one. Okay, that's not terrible, but it's an important detail to note as we're going through. And then lastly, it doesn't have any inherent built-in support for batch processing. Wouldn't that be nice if we could maybe speed this up by getting 10 things at a time instead of doing one at a time? But Rabbit doesn't really support that inherently, so okay. But we've got these cool things called fibers. And we really think fibers can work here. So if you've never played with fibers, A, you're probably lucky. And secondly, fibers are kind of like threads, except they exist in the same stack as your main application. So what Ruby actually does internally is it creates a single stack frame for the fiber. And for each fiber, it gets its own stack frame. And so it's able to just jump back and forth in its own stack to switch between fibers. This is much faster than context switches and threads. This is much lighter weight than forks or anything else. Also, because you're in one stack, you don't have to worry about the same kind of thread, mutex, crosstalk nonsense that you're always fighting, because you can't ever end up in another place in the stack. We only have one stack. We can't ever end up in those terrible, terrible places. So that's pretty cool. Now, because we're only in one stack, if we're bound on CPU, this doesn't do us any good, because we can do one thing and wait for it to finish, and then we can do the other thing. Well, that's not really concurrency. That's just the same thing we had before. But if we're waiting on I/O, we can actually leverage fibers in a really neat way and say that we're going to send off this data to the server, and instead of waiting for it to come back, we're going to go do something on that other fiber. And we'll come back and check on this guy later. And we can keep doing that and run hundreds or even thousands of fibers concurrently, because you can get an amazing amount of work done in the 20 milliseconds it takes to make that network request. This is really, really cool. So really, fibers are great for these asynchronous workloads. This is really handy. Sounds perfect. Except, always a problem. So fibers have this little thing. So if you think back to just a second ago, we're talking fibers are allocated on the main stack. That makes them really fast. It avoids, a lot of the other pain. But Ruby has a fixed size for an individual frame on the stack. And depending on your Ruby version and which bugs it has in the 1.9 branch, the size of that stack frame varies. But it's also really small. It's small enough that you probably can't save an active record object inside of a fiber. The callback chain inside of an active record call can easily be deeper than the amount of stack you have inside of one frame in Ruby. This hurts. You're going along in your application, and then suddenly, bam, system stack error. Cool. That was helpful data, Ruby. Thanks. I appreciate that. So on down from that, you also, we talked about fibers being great when you need the I/O stuff, but it kind of sucks to handle that yourself. So you kind of want to find some sort of a framework or toolkit that manages those I/O switch-offs for you. At the time, we evaluated and went with Event Machine, which creates kind of an event loop and lets you do some neat things with callbacks, and it's really nice. But it also means all of your I/O has to know that it's being dealt with inside of a fiber, because it has to know when to make those trade-offs and when to say, hey, I can get out of here. So your code isn't really agnostic to this. Your code has to know that it's running inside of these things. So it's not a really easy thing to just kind of slip into your application. And then along with that, there was a really nice set of tools around Event Machine called Synchrony. And it lets you avoid callback chaining and a lot of the mess you end up with in evented code. And it is the most complex bit of Ruby code I've ever seen. And we stumbled into a couple of bugs in it, and it was somewhat harrowing to go resolve. And then lastly, system stack error again. Man, these things are awful. And not only are they really hard to expect or to predict or to know what's going to happen, but Ruby really doesn't want to help you with this. So when you get a system stack error, you get one line of backtrace. So we're all used to being able to see the full backtrace of everything that just happened when we get an exception. One line, and that is the line that you blew the stack on. It could be 20 method calls deep in a library you didn't know you were using on a line of code you had no idea was going to happen. That's all the data Ruby gives you. There's a bug filed in Ruby to resolve this. It's been there for about 4 years, so I wouldn't hold your breath on that one getting solved anytime soon. So let's kind of move on. What did we really learn for this? Well, if we're going to be running somewhat arbitrary code, fibers are not going to be good for that, because we can't control that environment well enough to make sure we're staying inside of the stack and that we have the right network libraries enabled and that everything's ready to play all nice. We also learned as we went through this that RabbitMQ is actually pretty complex. To get the trade-offs of durability and availability and clustering, it took a lot of work. It took a lot more work than we expected it would take to get all of those things fit together. And really, we should have looked harder at celluloid. So celluloid is another common fiber evented choice. And we really should have looked harder at that, because at the end of the day, I think it simplifies a lot of the things that get hard in Event Machine. All right, so we're done with Rabbit. We got all this up, and honestly, it actually all works. And it's all running, and it was a little rocky, but we got there and we're cool. So now we need to go tackle our general purpose jobs. So let's talk a little bit about what it takes to process jobs with SQS. As usual, there's nothing. In fact, I doubt anyone in this room has hardly used SQS as a job processor. There is nothing in Ruby that does this. It is just shocking. So let's go build it. And I mean, we learned our lessons the last time. We can do this. This will be easy. So SQS is a really slick system. Like everything else Amazon does, it's an HTTP-based API. You make calls to it, you push some data, you make a call to it, and you request some data. Like all HTTP things, that means it's synchronous, which also adds a little bit of latency. So because we have to wait on those requests to come back, a call to SQS can be maybe 20 milliseconds to do a write. That's a little bit longer than we would probably prefer, but we can probably get away with this for now. But it does have some really nice things in that it will allow us to do batch processing built in. We can send it batches of varying sizes, and it will treat all of those as a batch of messages, and it will let us fetch them back down as a batch of messages. But not necessarily the same batch we sent in, but that's okay. We can just kind of parallel these requests and get a lot more done in that 20 millisecond window. So it probably balances out okay. So let's talk about concurrency again. So we realize for general purpose jobs, fibers are probably not it. So now we're down to our two choices of forks and threads. So why not threads? Well, I think everybody here has read, heard, seen, been berated about Ruby's global interpreter lock. It does kind of suck. It keeps you from being able to actually run threads completely concurrently. The Ruby VM blocks on certain operations and will not let you have two threads actually operating at exactly the same time. But it can interleave those two things in ways that may get you close. Other reasons threads are scary, so we have a legacy application. It's several years old. Is it thread safe? I don't know. I don't know if every gem we're using is thread safe. I don't know if we're using them all in their thread safe ways. I also don't want to be the one who has to find that out. That is a difficult problem to go solve. So thread safety is a little concerning here. And then lastly, general purpose job queues can have memory bloat. We're going to be fetching a lot of data. We're going to be doing a lot of possibly dumb things in our jobs because we didn't want to do these concurrently in a request. So this process could grow pretty big. And historically, Ruby will let you grow that process really big, and then when you're done with those objects, stay really big. That's not awesome. So threads don't give us the ability to get rid of that extra memory growth easily. I'm hopeful 2.1 makes all of this better with all of our great new garbage collection stuff, but at this point, we're just barely on Ruby 1.9. I mean, we already think we're in much better shape than we were in 1.8, but this is still concerning. Okay, so we're not going to thread our job processing. I guess that means forks. Okay, forks are kind of boring, but we're all used to forks, right? Like, these have been around forever. Some of the systems we all use all the time anyway, fork all the time. Resque, notoriously, is a forking job system, and Unicorn, which is a really solid Ruby web server, is built around, forking behavior in Ruby. So this has to be a well-worn path. We've got to be in good shape. This should be easy. Let's do this. So let's talk about how we can make our SQS job processing work for us. Let's start by fetching with threads. I know, I just got done telling you we can't use threads and threads are terrible. We can't use threads to actually process the jobs. That's scary. But if we want to use threads to just get more data out of SQS faster, that's okay. And in fact, we can avoid the global interpreter lock problem because this is all I/O. We're spending 20 milliseconds sending a request to SQS and waiting on data to come back. While that's happening, we could send 5 other requests to SQS and get more data. So we can fan that out quite a bit wider in a single process and not have to fight a lot of the crazy thread safety issues because this is isolated from our actual code. Then once we get that list of messages down from SQS, let's go ahead and fork a process with those messages. So this gives us a really nice way to manage that memory bloat I was talking about. So we'll process that batch of messages, and when that batch of messages is done, that child process will just die. So any memory bloat that child process gained during its hopefully short lifetime is gone. And we're back to just a small, sane little Ruby process. So we can actually manage this pretty well. And we can get a lot of these going at one time. And then, because we're building distributed systems here, we're going to do what all the cool distributed systems do, and we're going to have our own internal stats. So we're going to have a little web server that runs on a thread, and we can hit it, and it'll tell us how many messages it's processed and how many have errored out and what its throughput looks like and what the health of the system is, and this will be really cool. And then we can have a nice dashboard that aggregates this from all of these different processes on all these servers, and this is a great idea. Okay, so maybe it's not a perfect idea. So we run into some problems pretty quickly with this approach. First, pipe processing is actually really slow. You would think for something that is an underpinning of the Unix way that it would be faster. The answer is no, it's not. It's slow. In fact, we could only get about 6 child processes open before the data going back and forth between the processes was taking up about 98% of our CPU. That meant we had no time left to, do work or fetch more jobs. So our throttling was actually based on the faster we got, the slower we got. This is a bad trade-off. This does not work. So we're going to have to do something about that. And then we're running into this odd issue where occasionally the child processes just hang. They just don't respond. They begin taking up 0 CPU. They're stopped at whatever memory they had at that moment. They're writing no log output. They're doing nothing. They're just there. They don't respond to signals. Nothing is happening. They're just hanging. we don't know what's going on. Google around and you can see that there's some issues that both Resque and Unicorn have had when integrating with New Relic that maybe are related because we're doing something similar. So this is maybe it. All right, so a couple more weeks and we're still doing this, and we decide to just throw away this whole pipe processing stats nonsense. We're not that cool and it's not that useful. So we'll just add some more New Relic integration, tie into our internal monitoring system a little better, and this will be fine. We still can't reproduce this hanging issue. It's there and it happens a lot, but we can't reproduce it under controlled conditions. We can't actually make this happen when we want to. And it turns out debugging running Ruby processes is really hard. PryDebugger and a lot of those tools are really nice when Ruby's responding. If you're deadlocked or you have something else going on in that process, you have no way to get into it. So one of our engineers who's way better at C than I ever want to be started just running the process and jumping in with GDB and poking around at what was happening inside of the process and inside of the Ruby VM at the moment it was hung. And that's when we found some really interesting stuff. So it turns out Ruby had a little race condition in the early branches of 1.9.3. And what would happen is if you had any mutex lock in your parent process that was open when you forked, there's clearly a problem there, right? So we have a lock, we're now running some other set of code. We have no way to go back and release that lock. So Ruby helpfully knew that this would be a problem, and it would release all the locks as soon as you forked a child. So in the child process, one of the first things it does when it bootstraps that process is to remove all the mutex locks. They don't mean anything anymore, so we'll just get rid of them. But it had a little race condition that turned out if you forked a couple of processes at nearly the same time, it didn't do that. So what you ended up with were processes that were literally dead from start. They could not interact with their code. They couldn't do anything. So that's a real problem. Then we were using the Rails Express patch set, which back in the day was the only way to get good garbage collection in your Ruby app. It was, I think, the set of patches that went into Passenger at one point. There's a long history of these things floating around. And this was fine, but it had another bug fairly similar that would cause deadlocks. And then lastly, and this one is really my favorite because it's just staggeringly weird that it never came up before, Ruby's DNS resolve library is written in C because you want it to be really fast. And it uses the system calls for looking up DNS addresses and giving you IP addresses and doing all of that fun stuff. But it dropped into C in a way that didn't release the GIL, which meant every time you request a DNS address, for the entire length of that DNS request, your process is locked. Nobody else can do anything, and they're waiting on that to come back. So if you have a slow DNS request or a minor network blip or any number of things that will occur hundreds of times, your process just hangs out there for a while. That's real bad. And it turns out the solution, which is never the solution in Ruby, was to rewrite it in Ruby. The solution to make a slow C library faster was to rewrite it in Ruby. And the reason for that is the Ruby code doesn't trip the GIL. Since it never goes down to a system call and it just uses Ruby's native I/O libraries to do the DNS requests, it never actually locks the interpreter. So it ends up actually being way faster if you're doing anything concurrently. If you have more than one thread in your application, this library should be installed because it absolutely makes a difference. But this was just really surprising. So if you're following along, that means inside of basically a month of debugging, we have now come across 3 Ruby bugs, and one I didn't break down because I don't understand it, but we ran into a small bug in glibc over a particular range of patches, which were the default installed on some version of Ubuntu, where creating a fork was significantly slower than it should be by like 100x. Who knew? Turns out the fix is upgrade glibc. because we usually look for that. If you're interested in these things, the engineer who did most of this wrote up a really nice post in the Resque project on one of their issues, which was related to all of these same sorts of problems. So I encourage you to go look at that and see a little more detail about those things. So what did we learn when we got through SQS? Because we built the thing, we got it debugged, we got it running. We chose the safest set of things that we could, and it's still really hard. Scale is hard. And we have somewhat of a motto in our office, and it's something you're likely to hear us say regularly, and that's the naive solution fails fast, instantly. And this was another example of that. We thought we were doing something straightforward and easy, but it turns out that the subtle differences in the way we were doing it versus Resque versus Unicorn were leading us to really edge case problems that weren't really edge case for us anymore. These are really significant things. Also, debugging Ruby systems code is hard. We don't have good tooling for it. I recommend reading up on GDB and actually learning how to poke around a running Ruby process that way. There's an amazing amount of things you can learn from that. And Ruby actually internally provides some tools when it's running under GDB that will let you do things like run Ruby code from GDB and see results. We didn't know any of that before we started this, and that was some really helpful stuff. And then lastly, sometimes the bug really isn't your bug. I don't know how many hours we spent poring over all of our code, but we tore it inside out. We had logging on every statement. We were timing all sorts of requests. We knew every detail of everything, and it still wasn't working right because it turns out Ruby was broken. It wasn't our bug. But we wouldn't have been able to get to that point if we hadn't done the other work. But at some level, things can be broken. And when you start getting to significant scale and processing things at really intense speeds, you will find issues that are not yours more often than you would think. So what this boiled down to is that we actually wrapped up all of what I was just talking about into a library. It's a library we call Chore. It uses the same serialization format as Resque, which Sidekiq also uses, so it's a simple little JSON hash. That's what we pass across the wire into the queues. It lets us do some of the things we had problems with, like being able to configure per job what should happen, being able to scale things up per job. These were real problems. We can control per process and therefore per server what queues to listen to, what priorities effectively to listen to those on, and how many resources to devote to that. Also, because we're engineers and we don't like solving the same problem 3 times, it's agnostic to queue and to concurrency option, which means you can plug in different queues to it. It is designed in a way that you should be able to plug in multiple queues, and we already have 2 implemented in there right now. And then lastly, if you actually are lucky and have an application that's thread safe and doesn't do crazy memory intensive things, you can run it threaded, which will actually be faster than going through the forking method of processing your jobs. The downside there is it's not released yet. It's coming very soon. We're going through our internal process of getting all of that open sourced, so that should be available soon. So let's look back and let's look at the issues we had when we started, and let's talk through what those are. So our job queues are backing up. Well, we pretty well solved that. We have a job processor that's much faster. It's much faster than our old one. Event processing is a little lossy. Well, we replaced all of that crazy syslog stuff with RabbitMQ and our new Rabbit job processing stuff, and we're actually able to track these and know if we were losing messages, how many we were losing, and the answer is 0. So that's good. We've solved that. Sadly, we still built all this ourselves, so we still own the burden of all of this and the debugging burden of all of this. So we didn't get out of having everything homegrown, but we do at least feel like we got to things that are well designed and well understood, and a little less, have a few less years of pain piled on top of them. Went through the last 2, we can actually scale up our jobs individually, we can manage those in ways that are sane. And then the great part is, so, now we're here, it's 2014, which is crazy, but we're at more than 2x the amount of traffic we were processing before. So we're processing millions of event millions of events through this system per minute. Millions. We're processing well over 1 million of our general process jobs per hour. This stuff's running at scale, and it worked. So we designed something that fit our scale in 2012. We're here a year later, and it still holds up. That's really exciting as someone who got to be in the middle of building all of that. That's always your hope, is that you've got it figured out, and so far that's gone really well. So we're really excited for that. So kind of in conclusion, what do we know? Job processing's hard. We thought it was not that hard. We thought we kind of understood this, but really things are hard. And at scale, everything is hard. Even things like looking up a DNS address apparently are not trivial. You can assume nothing at scale. That was a painful lesson to learn, because you don't assume that looking up a DNS address is going to be your biggest problem. And it wasn't our biggest problem, but it was a big one, and we had no idea that was coming. Also, we didn't treat all of our jobs the same at the end. We determined we had really different use cases and really different queue technologies and really different trade-offs that we needed. We didn't end up in a place where everything was doing exactly the same thing, and we were okay with that. That gives us a lot more flexibility to go forward and a lot more options on how we manage this later. And lastly, we understood the trade-offs. So we got through our RabbitMQ stuff, and we understood what trade-offs we were making for durability and performance. We understood when we took SQS that we were taking a slight total throughput hit to get really great availability numbers and really great durability that we didn't have to manage. And a throwback to our bonus cart, we also understood the cost flow of these things. We understood what it was going to cost to build these things up and to scale them out as they went. That was one of the things we actually really liked about SQS, is that it's incredibly cheap. Since you pay per message, it just scales exactly as your load does. There are no big incremental jumps as you have to go add a second cluster or just add more nodes into the cluster. It's just straight linear with as much traffic as you want to throw at it. We treat it kind of like a magic bucket. It takes 20 milliseconds to send stuff into. It takes 20 milliseconds to get stuff out of. We haven't found the next step. We haven't found that point where we can throw so much at it that it now takes 30. We haven't found it, and that's fantastic. So those are some really, really interesting trade-offs and things we're really happy with that we ended up with at the end. So if any of that sounds really interesting, we're, like lots of people here, are hiring. Either come find me later or check out our job site. That's it. Thank you, guys.